Okay, another chemistry video for AAQ chemistry. This one's about electronegativity. So there's a hydrogen fluoride, HF, and there's a covalent bond between them. Now, if we look at the two electrons in the covalent bond, we're not bothered about the other electrons, yeah? What we call the lone pairs. There are three lone pairs, aren't they? Not worried about them, just the two electrons in the bond. Now, if you were those electrons, would you be more attracted to the fluorine or to the hydrogen? And the answer is to the fluorine. Okay, the fluorine atom is more electronegative. And electronegativity, it's how attractive an atom which is involved in a bond is to the electrons in that bond. Okay, so the electrons in the bond will spend more time around the fluorine atom than the hydrogen atom. If you remember a couple of videos ago, I talked about kind of probability of where you'd find an electron. And there's more probability that you'll find the electron mooching around the fluorine atom than the hydrogen atom because it's more attractive. Okay? And so what will happen is that end of the molecule will become more negative. And this is how we represent it. This little arrow thing below, okay, this thing here. So you've got a positive end of the molecule, which is sigma plus, and the negative end of the molecule. If you look at the arrow, you see on the left-hand end, that looks like a little positive sign, doesn't it? Okay, so the molecule has got a positive end and a negative end. We say it's a polar molecule, yeah? Polar, so it has a positive pole and a negative pole. Pole means ends, like the North and the South Pole. Yeah, nothing to do with magnetism. Yeah, but it's a positive end and a negative end. It is a polar molecule. It has a dipole. Now, the electronegativity of an atom is how attractive it is to the electrons in a shared bond. Okay, now what will it depend on? You know, why is the fluorine atom more electronegative? It depends on the number of protons in its nucleus. It will depend on the distance between the bonding electrons and the nucleus, and it will depend on whether there are any shells which are shielding the attractive force. If there's shells in the way, then that makes the force weaker. So we can actually give a number to electronegativity. It's called the Pauling scale. And if you look at these, at the periodic table, and look at the numbers here, what patterns can you see? Yeah, first of all, what patterns can you see? Look at periods 2 and 3. Yes, what patterns can you see in electronegativity? And do you think you might be able to explain why? Okay, if you look at period 2, the least electronegative is lithium. The most electronegative is fluorine. Why? Okay, so as we go across a period, like again, look at period 2, look at period 3, the electronegativity increases. Why does it increase? Because the number of protons is increasing. As the atomic number gets bigger, that means you've got more and more protons, so the nucleus is more and more attractive to electrons. Okay? Note that most of the noble gases don't actually do any bonding, so they're irrelevant, not applicable. Krypton and xenon apparently do a bit of bonding every now and then, but helium, neon and argon, no, forget it. So they don't count. If we go down a group from lithium, sodium, potassium, going down a group, electronegativity gets less, it decreases. Now why? Because the atoms are getting bigger, So the distance of the bonding electrons to the nucleus is getting bigger. And also you get more and more shells. Yeah, lithium has got 2 shells, sodium has got 3 shells, etc. And as I've said, the shells kind of make the attractive force weaker. So electronegativity decreases as the atoms get bigger and the number of shells increases. Now look at this. When atoms with different electronegativities bond, then we get a dipole. In other words, we get a polar molecule, a dipole, like a positive pole and a negative pole. And the bigger the difference in the electronegativity, then the bigger the dipole. So we gave these numbers to electronegativity. Hydrogen is 2.1, fluorine is 4. So there's quite a big difference. So you're going to get a strong dipole with the fluorine being negative. One interesting thing is that if the difference in electronegativity is big enough, yes, if you look at sodium and chlorine, what actually happens is that the chlorine takes the electrons all to itself and you end up with an ionic compound. Apparently, if the difference in electronegativity is greater than 2, then you don't get a covalent bond, you get an ionic bond, because the more electronegative atom just takes the electrons all to itself. Which of these molecules will be polar? See if you can figure it out for yourself. I've given you the formula, yes, and I've given you the electronegativities of the atoms involved. So see if you can figure out for yourself. So pause the video, have a little think. I'll show you the answer in 3, 2, 1. So first of all, well, in fact, here are the answers. Right, first of all, the carbon dioxide. Well, the oxygen atoms are more electronegative, but there's 2 of them and they are pulling in opposite directions. So it's nice and balanced. There isn't a positive end and a negative end. So that's no. Remember, with the carbon dioxide, there's actually 2 double bonds, isn't there? So carbon dioxide is no. Chlorine, Cl2, no. Why? Because you've got the same atom. And so it's nice and balanced. You're not going to get a positive end and a negative end. So diatomic elements like chlorine and nitrogen and oxygen, no, they are not polar molecules. The methane, CH4, that's methane, no, because you've got the 4 hydrogen atoms. Now, they're not pulling in opposite directions. The molecule is tetrahedral, but the resultant pull, if you add together all of the pulls, it is 0. Yeah, so they are pulling in such a way that all the forces cancel, and it is not a polar molecule. Whereas the one below is, and that is chloroform. And basically what you can see is we haven't got 4 hydrogens, we've got 3 chlorine atoms and a hydrogen atom joined to the carbon. And the chlorine atoms are more electronegative, so that's going to pull the electrons down a bit. So we're going to get the bottom of that molecule being negative. So that is a polar molecule. H2O, yay, water. And we know that that is a polar molecule, okay? Because the lone pairs, that's the effect of the lone pairs there. And they're going to repel the 2 hydrogen atoms downwards, and we're going to end up with a polar molecule. And NH3, and that is polar as well, and you can see the effect of the lone pairs there, pushing the hydrogen atoms down, forming that, was it trigonal pyramidal molecule, or pyramidal, whatever. So that is going to be polar.